The next paper is entitled A Simple High-Precision Method for Extrapolating Sat-AIS System Performance. The authors are Emiliano Re, Valentin Boissineau, Alberto Ginesi, and Caster Tauben from ISA-EXTEC. Emiliano graduated in telecommunication engineering at the University of Rome Tor Vergata and received a PhD degree from the same university on the use of LTE for mobile satellite services. From 2007 to 2009, he has been working with OHB Italy, mainly on Sat-AIS related topics. At the end of 2009, he joined the European Space Agency, working in the RF Payload System Division in the Technical Directorate in ESTEC as a communication system engineer. His main areas are broadband and mobile satellite communication systems and search and rescue satellite systems.
Thanks, Mr. Chairman, for the introduction. Good morning, everybody. So here I'm going to present a method which we devised for extrapolating Sat-AIS system performance. Let's say, and the objective was to make system simulation faster than what we can do today. So just the table of content of this short presentation. I will very quickly introduce the Sat-AIS system. Then I will present what are the typical methods used today for characterizing the end-to-end system performance of Sat-AIS systems. And then I will introduce the method which we devised along with the performance analysis. And finally, I will draw some conclusions from this exercise. So as we know, the AIS is a system for surveillance and collision avoidance for maritime traffic. And it's based on the transmission of AIS messages containing some information about the vessels itself, of course, depending on the type of message. So this terrestrial tool is limited in range by the radio horizon. So there was this idea from the satellite community several years ago to try to detect messages from space so that you could have a kind of global picture of the maritime traffic. So one of the main tasks for designing a satellite AIS system is indeed the characterization of the end-to-end system performance. And this characterization is particularly critical because due to the complexity of the system, this may take a long time. And this is very critical, especially in the design phase where you want to trade off different architectures. And then you cannot afford a very long simulation time. So in the performance characterization for the full system, usually there are two performance parameters which are assessed. The first one is what is called time update interval, which is the time difference between successive messages detected from the same vessel. The second figure of merit is the timeliness, which is the time delay from the time when the message is transmitted to the time when it's available to the end user. So while the second figure of merit is strictly dependent on the geometry of the system, so on the orbits and the ground segments, the first parameter is very much dependent on the detection performance of the system. And what we assess is actually the long-term statistic, which means that for making it stable, we have to simulate a simulation time which is long enough for having this long-term statistic. So the reason why we started investigating this topic came out during an exercise which we performed in ESA, which was the comparative performance assessment. So we started this exercise in 2011. Basically, there was an open call where we were asking anybody to propose some satellite-based AIS system along with all, let's say, the parameters of their proposed system. Then we were running, using some tool available at ESTEC, system simulation, and then we were producing the baseband signals as seen by every antenna of the proposed system. Then we were sending this huge amount of data to the participants, and they were running their own algorithms, both for the beamforming and for the receiver. And then they were sending back to us the messages which they were seeing, and we were comparing what we transmitted in the simulation with what they saw to determine these parameters. And we realized that it will take a lot of time to do this kind of characterization. So due to the fact that the Sat-AIS has been gaining momentum during the last years, we saw that there are available different proprietary system simulators. And these simulators usually have a common structure, which is that indeed every simulator is able to simulate the satellite orbits using some propagator. They simulate the vessel traffic on ground and the full transmission of the AIS messages, which means simulating the RF characteristic of the transmitters and the physical layer and the MAC layer of the AIS stand specification. Then, combining the transmitters with the geometry of the system, this simulator compute a link budget to determine the radio environment on the two AIS channels on board the satellite. And then there is let's say, the part where we saw differences in the different simulators, which is the modeling of the payload. With the payload, I mean the onboard antenna plus the detection part. We can identify more or less two main strategies which are currently used. The first one we call physical layer abstraction. So in this case, the receiver is characterized as a physical layer people usually do, which is by means of the packet error ratio as a function of the C over N and the C over I seen at the receiver input. So basically in this strategy, the system simulator will import some lookup table with this kind of performance, and then depending on the link budget computation, you can come out with a packet error ratio for that specific message. In the second approach, which is actually what we use during the CPA, we have these full processing simulations, which means that we go down to the generation of the baseband signals, and then we go through the actual processing of the signals. So indeed, we have pros and cons of the two approaches. The physical layer abstraction is indeed a very quite fast method. So it's, let's say, more probably better for running trade-off. But the problem is that the accuracy of this modeling can be limited. And the second point is that it's quite difficult to simulate adaptive beamforming algorithms. On the other hand, the full processing approach is very accurate, and actually it's the most accurate you could think of when you have to do a simulation, because you go through the whole chain. Then indeed the accuracy is depending on your models, but still it's the best approach you can use in terms of accuracy, but it's extremely slow. So what we were trying to achieve in this work was to find out a method which was at the same time fast and accurate enough for carrying out this characterization. So this is a block diagram of our approach. So still, the approach we tried to assess was based on a full system simulator. So with the same, let's say, simulation blocks of the other simulator. But the main point, the main novelty that we try to assess is a different modeling of the payload on board. So we try to mix the two approaches, the physical layer abstraction together with the full processing approach. In particular, we have a two-step approach. In the first step, what we do is to run a smaller full processing simulation. And in particular, rather than simulating the full constellation, we just take one satellite and we run a full processing simulation for a limited amount of time, typically a few orbits, so a few hours. And then we characterize somehow the detection performance of the payload. We will see how, because we assess different methods for that. In the second step, instead, we do the actual system simulation. So what we do is we perform the link budget for every message, and then we use this characterization of the payload, which, as I said, is the central part of this method. So the way we are modeling the payload is based on somehow determining the probability of detection per message as a function of some variable, which is the number of messages we received within a certain time window. We will see later what we assessed. The important thing that we noticed is that this performance of detection curve is not constant over time, and despite the number of messages you receive. And the explanation for that is that even if you have the same number of ships within the field of view, you can have very different cases. Imagine, for instance, a case where your satellite is overflying an ocean, and then you have a certain number of ships, and in that case, you can assume pretty much that these ships are distributed in a uniform way within the field of view. In a second case, for instance, you are overflying a coastal region, and in that case, you can expect that the traffic is very concentrated in a smaller area. So what you can expect is that in the first case, in a uniform traffic case, your antenna can discriminate quite well the different messages if it's directive enough. But in the second case, since all your messages are coming from a specific direction, you will never be able to isolate them with the antenna. So we tested different approaches for this characterization. In the first case, we were using the probability of detection curve, just one curve all over the globe, as a function of the number of messages received within 10 seconds. So this speeds up the simulation very much, because you have just to find out one probability of detection value for every satellite in 10 seconds, and then you can use that for all the 10 seconds. In the second case, we reduced this window to a single time slot, but still we were using a single probability of detection curve all over the world. Then we realized this thing of the, let's say, time variation of the probability of detection, and then we started using different probability of detection curves in different areas. So in two different ways. In the first case, we were characterizing this curve as a function of the number of messages received on the sum of the two AIS channels. In the second case, we were characterizing separately the two AIS channels. So the performance analysis of this technique we show here is coming out from a comparison of the full processing simulation we did against this extrapolation method. And in particular, we are using the system which was proposed by ISIS, which is a Dutch company, during the CPA. And the system they proposed was composed of 16 satellites. Here you can see the ground tracks during 1 hour. So these two plots are the cumulative distribution functions of the time update interval of the system. On the left hand, we have the picture showing the time update interval on the world, whereas in the second picture, we are just considering what we call the high traffic zones. So on the left picture, you can see that the different techniques we propose have got pretty much the same performance, and the red curve is our benchmark, which is the full processing simulation. So you can see that we can achieve more or less a 5% accuracy in the CDF of the time update interval. So these techniques perform pretty much in the same way. But if we go to analyze what happens just when considering the high traffic zones, which are actually the most critical part for your system design, then we see a very different performance of the different techniques. And in particular, what we saw is that the accuracy of this method is very good, and in particular is within 5% from the full processing approach, when you consider the geographical correlation of detection performance. Whereas when you don't consider this and you're just considering a single probability of detection curve all over the globe, your accuracy goes down to 15 to 20%, which is, let's say, not really acceptable when you design a system, because you could come out oversizing or undersizing your system. What I want to show also is the performance when you consider a very small area. So in this case, we are just considering the Mediterranean Sea. So in this case, again, the accuracy when you consider a single probability of detection curve is getting worse. Whereas when you actually differentiate the different detections over different areas, your accuracy is still good enough and is still around 5%. So out of the 4 techniques we analyzed, we found out that the best approach for this extrapolation is to consider the probability of detection per area as a function of the number of messages summing the two AIS channels, because considering just one of the two doesn't really make a difference in terms of accuracy of your extrapolation, but it still allows to gain some simulation time. So what I show here on the picture is actually this probability of detection curve as a function of the number of messages per slot in the different areas. You can see that the blue continuous curve is the detection curve all over the globe. But if you go to consider the different regions, and all of the regions there are high traffic zones, you see that there is a different variation area by area. And this is exactly why, if you consider a single detection curve, your accuracy is not good enough. Then we analyzed the limitations of this model. And in particular, what we cannot simulate, what we cannot model, is the time and space correlation of the detection. So we went to see, again comparing the results with a full processing simulation where this effect can be considered, what is the effect of this correlation and what is the error that we are introducing in the extrapolation. So the first analysis is about the time correlation of the detections. So what we mean is that in our simulation, in our extrapolation, we are assuming that two different messages are, from a detection point of view, uncorrelated. Whereas in practical case, it may happen that a vessel is in a very unlucky area, and you will never be able to detect that because you always have a lot of colliding messages. So what we assessed is, over the simulation time, what is the relative difference between the number of undetected vessels with a full processing approach and with our extrapolation. And actually, what you see in the different areas is that the difference is increasing over time, which is that our extrapolation cannot be scaled for an infinite time. But still, when you compare the system results, you can see that in our case, we consider a 24-hour simulation, which is good enough for assessing the statistics of a constellation. The error which is introduced is quite limited because the full accuracy is 5%. But we can actually see that most of this error is due to this effect. When we go to, instead, to assess the space correlation, so what we mean here is that the detection from different satellites in our extrapolation are considered uncorrelated, whereas they are in reality correlated, because imagine that you see the same transmission from two satellites which are very close to each other, then the interference environment is correlated, and anyway you will see the same number of colliders, so there is space correlation. So the analysis is done in the same way, which is we assess what is the percentage of undetected ships considering different numbers of satellites, so from 1 to 16. And what we see in this case is that this difference is not varying. So this means that at least up to 16 satellites, we didn't see any space correlation. So the space correlation is not affecting that much our performance. It is important to notice that these 16 satellites were distributed on 4 orbital planes. Indeed, this space correlation we expect being correlated to the number of orbital planes. So the closer the orbital planes, the higher the space correlation. So the important thing that we can conclude from this is that this extrapolation method is able to achieve quite an high accuracy, within 5%, which we consider very good for a system design. And the remarkable thing is the time that we save with this approach. So from our experience with the CPA, we can say that for doing a system simulation, we were taking, with a full processing approach, we were taking from 2 to 4 weeks for a single simulation, which is extremely long. Whereas with this method, we were able to run system simulation within a few hours. And even with the physical layer approach, which is often used, the typical runtime is some days. So still we are gaining in time, in runtime, even against the physical layer, whereas we are achieving a very good accuracy. So for concluding, we want to acknowledge all the participants to the comparative performance assessment, because this exercise actually allowed us to, let's say, test and verify this method in different scenarios case, because we could compare it with a full processing approach. And in particular, we wish to thank ISIS for allowing us to publish their system results. So if you have any question, I'm pleased to answer.
If I well understood, the limitation you have identified is that when you evaluate an instantaneous probability of detection, you allocate the same to all the ships on the slot. Maybe have you considered the idea to either to consider the same probability for all ships, to have a law to establish different probabilities for the ship that would be in average the value you had? Something like if you have a probability of 10%, have a law that says that one ship among 10 will have a detection of 80%, one 20%, have a distortion like it to avoid your point, your limitation.
So what we did, I'm not sure 100% that I understood your question. So you're asking me whether if we thought about introducing some, let's say, variation of the detection probability per vessel within, yes. So actually we did it. In the first place, we tried also to assume that the probability of detection was had a Gaussian distribution within the field of view with a certain sigma. But what we saw actually that we were not increasing the accuracy, but on the other, actually we were making the accuracy worse. So in the end, we decided to keep the same probability of detection per ship once you define the number of messages you receive.
Other questions? Is there any way to take into account the time correlation?
So there could be. We thought about it in the beginning, and that would be, let's say, flagging some ships as undetectable. In practical terms, what you could do is that after the first passage, you see the ships that you never detect. And then you need a second probability of detection curve, which is conditioned to the fact that you didn't receive the messages in the first passage. So we had also this idea, but we didn't implement it because the accuracy that we achieved was good enough for us.
Yeah.
Yes.
Thank you very much, Emiliano.
Thanks.